Chapter 12 of Introduction to Mathematical Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. Selections and the multiplicative axiom. In this chapter, we have to consider an axiom which can be enunciated but not proved in terms of logic, and which is convenient, though not indispensable, in certain portions of mathematics. It is convenient in the sense that many interesting propositions, which it seems natural to suppose true, cannot be proved without its help. But it is not indispensable, because even without those propositions, the subjects in which they occur still exist, though in a somewhat mutilated form. Before enunciating the multiplicative axiom, we must first explain the theory of selections, and the definition of multiplication when the number of factors may be infinite. In defining the arithmetical operations, the only correct procedure is to construct an actual class or relation, in the case of relation numbers, having the required number of terms. This sometimes demands a certain amount of ingenuity, but it is essential in order to prove the existence of the number defined. Take, as the simplest example, the case of addition. Suppose we are given a cardinal number μ and a class a which has μ terms. How shall we define μ plus μ? For this purpose, we must have two classes having μ terms, and they must not overlap. We can construct such classes from a in various ways, of which the following is perhaps the simplest. Form first all the ordered couples whose first term is a class consisting of a single member of a, and whose second term is the null class. Then, secondly, form all the ordered couples whose first term is the null class, and whose second term is a class consisting of a single member of a. These two classes of couples have no member in common, and the logical sum of the two classes will have μ plus μ terms. Exactly analogously, we can define μ plus v, given that μ is the number of some class a and v is the number of some class beta. Such definitions, as a rule, are merely a question of a suitable technical device, but in the case of multiplication, where the number of factors may be infinite, important problems arise out of the definition. Multiplication, when the number of factors is finite, offers no difficulty. Given two classes a and beta, of which the first has μ terms and the second v terms, we can define μ times v as the number of ordered couples that can be formed by choosing the first member out of a and the second out of beta. It will be seen that this definition does not require that a and beta should not overlap. It even remains adequate when a and beta are identical. For example, let a be the class whose members are x1, x2, x3. Then the class which is used to define the product, μ times μ, is the class of couples, the ordered pair x1, x1, the ordered pair x1, x2, the ordered pair x1, x3, the ordered pair x2, x1, the ordered pair x2, x2, the ordered pair x2, x3, the ordered pair x3, x1, the ordered pair x3, x2, the ordered pair x3, x3. This definition remains applicable when μ or v or both are infinite, and it can be extended step by step to 3 or 4 or any finite number of factors. No difficulty arises as regards this definition, except that it cannot be extended to an infinite number of factors. The problem of multiplication when the number of factors may be infinite arises in this way. Suppose we have a class kappa consisting of classes. Suppose the number of terms in each of these classes is given. How shall we define the product of all these numbers? If we can frame our definition generally, it will be applicable whether kappa is finite or infinite. It is to be observed that the problem is to be able to deal with the case when kappa is infinite, not with the case when its members are. If kappa is not infinite, the method defined above is just as applicable when its members are infinite as when they are finite. It is the case when kappa is infinite, even though its members may be finite, that we have to find a way of dealing with. The following method of defining multiplication generally is due to Dr. Whitehead. It is explained and treated at length in Principia Mathematica, Volume 1, Stard number 80 and following, and Volume 2, Stard number 114. Let us suppose, to begin with, that kappa is a class of classes no two of which overlap. Say the constituencies in a country where there is no plural voting, each constituency being considered as a class of voters. Let us now set to work to choose one term out of each class to be its representative, as constituencies do when they elect members of Parliament, assuming that by law each constituency has to elect a man who is a voter in that constituency. We thus arrive at a class of representatives who make up our Parliament, one being selected out of each constituency. How many different possible ways of choosing a Parliament are there? Each constituency can select any one of its voters, and therefore, if there are mu voters in a constituency, it can make mu choices. The choices of the different constituencies are independent. Thus, it is obvious that, when the total number of constituencies is finite, the number of possible parliaments is obtained by multiplying together the number of voters in the various constituencies. When we do not know whether the number of constituencies is finite or infinite, we may take the number of possible parliaments as defining the product of the numbers of the separate constituencies. This is the method by which infinite products are defined. We must now drop our illustration and proceed to exact statements. Let kappa be a class of classes, and let us assume to begin with that no two members of kappa overlap. That is, if alpha and beta are two different members of kappa, then no member of the one is a member of the other. We shall call a class a selection from kappa when it consists of just one term from each member of kappa. That is, mu is a selection from kappa if every member of mu belongs to some member of kappa, and if alpha be any member of kappa, mu and alpha have exactly one term in common. The class of all selections from kappa we shall call the multiplicative class of kappa. The number of terms in the multiplicative class of kappa, that is, the number of possible selections from kappa, is defined as the product of the numbers of the members of kappa. This definition is equally applicable whether kappa is finite or infinite. Before we can be wholly satisfied with these definitions, we must remove the restriction that no two members of kappa are to overlap. For this purpose, instead of defining first a class called a selection, we will define first a relation, which we will call a selector. A relation R will be called a selector from kappa if, from every member of kappa, it picks out one term as the representative of that member. That is, if, given any member alpha of kappa, there is just one term x which is a member of alpha and has the relation R to A. And this is to be all that R does. The formal definition is: a selector from a class of classes kappa is a one-many relation having kappa for its converse domain, and such that, if x has the relation to alpha, then x is a member of alpha. If R is a selector from kappa, and alpha is a member of kappa, and x is the term which has the relation R to alpha, we call x the representative of alpha in respect of the relation R. A selection from kappa will now be defined as the domain of a selector, and the multiplicative class, as before, will be the class of selections. But when the members of kappa overlap, there may be more selectors than selections, since a term x which belongs to two classes alpha and beta may be selected once to represent alpha and once to represent beta, giving rise to different selectors in the two cases, but to the same selection. For purposes of defining multiplication, it is the selectors we require rather than the selections. Thus, we define the product of the numbers of the members of a class of classes kappa is the number of selectors from kappa. We can define exponentiation by an adaptation of the above plan. We might, of course, define mu raised to the new power as the number of selectors from new classes, each of which has mu terms. But there are objections to this definition, derived from the fact that the multiplicative axiom, of which we shall speak shortly, is unnecessarily involved if it is adopted. We adopt instead the following construction. Let alpha be a class having mu terms, and beta a class having mu terms. Let y be a member of beta, and form the class of all ordered couples that have y for their second term and a member of alpha for their first term. There will be mu such couples for a given y, since any member of alpha may be chosen for the first term, and alpha has mu members. If we now form all the classes of this sort that result from varying y, we obtain together new classes, since y may be any member of beta, and beta has new members. These new classes are each of them a class of couples, namely, all the couples that can be formed of a variable member of alpha and a fixed member of beta. We define mu raised to the new power as the number of selectors from the class consisting of these new classes, or we may equally well define mu raised to the new power as the number of selections. For since our classes of couples are mutually exclusive, the number of selectors is the same as the number of selections. A selection from our class of classes will be a set of ordered couples, of which there will be exactly one having any given member of beta for its second term, and the first term may be any member of alpha. Thus, mu raised to the new power is defined by the selectors from a certain set of new classes each having mu terms. But the set is one having a certain structure and a more manageable composition than is the case in general. The relevance of this to the multiplicative axiom will appear shortly. What applies to exponentiation applies also to the product of two cardinals. We might define the product of mu and nu as the sum of the numbers of new classes each having mu terms, but we prefer to define it as the number of ordered couples to be formed consisting of a member of alpha followed by a member of beta, where alpha has mu terms and beta has nu terms. This definition, also, is designed to evade the necessity of assuming the multiplicative axiom. With our definitions, we can prove the usual formal laws of multiplication and exponentiation. But there is one thing we cannot prove. We cannot prove that a product is only zero when one of its factors is zero. We can prove this when the number of factors is finite, but not when it is infinite. In other words, we cannot prove that, given a class of classes none of which is null, there must be selectors from them, or that, given a class of mutually exclusive classes, there must be at least one class consisting of one term out of each of the given classes. These things cannot be proved, and, although at first sight they seem obviously true, yet reflection brings gradually increasing doubt, until at last we become content to register the assumption and its consequences as we register the axiom of parallels, without assuming that we can know whether it is true or false. The assumption, loosely worded, is that selectors and selections exist when we should expect them. There are many equivalent ways of stating it precisely. We may begin with the following. Given any class of mutually exclusive classes, of which none is null, there is at least one class which has exactly one term in common with each of the given classes. This proposition we will call the multiplicative axiom. Footnote 1. See Principia Mathematica, Volume 1, star number 88, also Volume 3, star numbers 257 to 258. End of footnote 1. We will give first various equivalent forms of the proposition, and then considers certain ways in which its truth or falsehood is of interest to mathematics. The multiplicative axiom is equivalent to the proposition that a product is only zero when at least one of its factors is zero, that is, that, if any number of cardinal numbers be multiplied together, the result cannot be zero unless one of the numbers concerned is zero. The multiplicative axiom is equivalent to the proposition that, if R be any relation, and kappa any class contained in the converse domain of R, then there is at least one one-many relation implying R and having kappa for its converse domain. The multiplicative axiom is equivalent to the assumption that if alpha be any class, and kappa all the subclasses of alpha, with the exception of the null class, then there is at least one selector from kappa. This is the form in which the axiom was first brought to the notice of the learned world by Zermelo in his Beweis, dass jede Menge vergrößert werden kann, footnote 1, Mathematische Annalen, volume 59, pages 514 to 516. In this form, we shall speak of it as Zermelo's axiom. End of footnote 1. Zermelo regards the axiom as an unquestionable truth. It must be confessed that, until he made it explicit, mathematicians had used it without a qualm, but it would seem that they had done so unconsciously, and the credit due to Zermelo for having made it explicit is entirely independent of the question whether it is true or false. The multiplicative axiom has been shown by Zermelo in the above-mentioned proof to be equivalent to the proposition that every class can be well ordered, that is, can be arranged in a series in which every subclass has a first term, except, of course, the null class. The full proof of this proposition is difficult, but it is not difficult to see the general principle upon which it proceeds. It uses the form which we call Zermelo's axiom, that is, it assumes that, given any class a, there is at least one one-many relation R whose converse domain consists of all existent subclasses of a, and which is such that, if x has the relation R to xi, then x is a member of xi. Such a relation picks out a representative from each subclass. Of course, it will often happen that two subclasses have the same representative. What Zermelo does, in effect, is to count off the members of a one by means of R and transfinite induction. We put first the representative of a, call it x sub 1, then take the representative of the class consisting of all of a except x sub 1, call it x sub 2. It must be different from x sub 1 because every representative is a member of its class, and x sub 1 is shut out from this class. Proceed similarly to take away x sub 2, and let x sub 3 be the representative of what is left. In this way, we first obtain a progression, x sub 1, x sub 2, and so on to x sub n, and so on, assuming that a is not finite. We then take away the whole progression. Let x sub omega be the representative of what is left of a. In this way, we can go on until nothing is left. The successive representatives will form a well-ordered series containing all the members of a. The above is, of course, only a hint of the general lines of the proof. This proposition is called Zermelo's theorem. The multiplicative axiom is also equivalent to the assumption that of any two cardinals which are not equal, one must be the greater. If the axiom is false, there will be cardinals μ and v such that μ is neither less than, equal to, nor greater than v. We have seen that Aleph sub 1 and 2 raised to the Aleph sub 0 power possibly form an instance of such a pair. Many other forms of the axiom might be given, but the above are the most important of the forms known at present. As to the truth or falsehood of the axiom in any of its forms, nothing is known at present. The propositions that depend upon the axiom, without being known to be equivalent to it, are numerous and important. Take first the connection of addition and multiplication. we naturally think that the sum of new mutually exclusive classes, each having mu terms, must have the product of mu and nu terms. When nu is finite, this can be proved, but when nu is infinite, it cannot be proved without the multiplicative axiom, except where, owing to some special circumstance, the existence of certain selectors can be proved. The way the multiplicative axiom enters in is as follows. Suppose we have two sets of new mutually exclusive classes, each having mu terms, and we wish to prove that the sum of one set has as many terms as the sum of the other. In order to prove this, we must establish a 1-1 relation. Now, since there are in each case new classes, there is some 1-1 relation between the two sets of classes. But what we want is a 1-1 relation between their terms. Let us consider some 1-1 relation S between classes. Then if kappa and lambda are the two sets of classes, and alpha is some member of kappa, there will be a member beta of lambda, which will be the correlate of alpha with respect to S. Now alpha and beta each have mu terms, and are therefore similar. There are, accordingly, 1-1 correlations of alpha and beta. The trouble is that there are so many. In order to obtain a 1-1 correlation of the sum of kappa with the sum of lambda, we have to pick out one selection from a set of classes of correlators, one class of the set being all the 1-1 correlators of alpha with beta. If kappa and lambda are infinite, we cannot in general know that such a selection exists, unless we can know that the multiplicative axiom is true. Hence, we cannot establish the usual kind of connection between addition and multiplication. This fact has various curious consequences. To begin with, we know that Aleph raised to the second power is equal to the product of Aleph and Aleph, which is equal to Aleph. It is commonly inferred from this that the sum of Aleph classes, each having Aleph members, must itself have Aleph members. But this inference is fallacious, since we do not know that the number of terms in such a sum is Aleph times Aleph, nor consequently that it is Aleph. This has a bearing upon the theory of transfinite ordinals. It is easy to prove that an ordinal which has Aleph predecessors must be one of what Cantor calls the second class, i.e., such that a series having this ordinal number will have Aleph terms in its field. It is also easy to see that, if we take any progression of ordinals of the second class, the predecessors of their limit form at most the sum of Aleph classes, each having Aleph terms. It is inferred thence, fallaciously, unless the multiplicative axiom is true, that the predecessors of the limit are Aleph in number, and therefore that the limit is a number of the second class. That is to say, it is supposed to be proved that any progression of ordinals of the second class has a limit which is again an ordinal of the second class. This proposition, with the corollary that (1), the smallest ordinal of the third class, is not the limit of any progression, is involved in most of the recognised theory of ordinals of the second class. In view of the way in which the multiplicative axiom is involved, the proposition and its corollary cannot be regarded as proved. They may be true, or they may not. All that can be said at present is that we do not know. Thus, the greater part of the theory of ordinals of the second class must be regarded as unproved. Another illustration may help to make the point clearer. We know that the product of 2 and Aleph equals Aleph. Hence, we might suppose that the sum of Aleph pairs must have Aleph terms. But this, though we can prove that it is sometimes the case, cannot be proved to happen always, unless we assume the multiplicative axiom. This is illustrated by the millionaire who bought a pair of socks whenever he bought a pair of boots, and never at any other time, and who had such a passion for buying both that at last he had Aleph pairs of boots and Aleph pairs of socks. The problem is, how many boots had he, and how many socks? One would naturally suppose that he had twice as many boots and twice as many socks as he had pairs of each, and that therefore he had Aleph of each, since that number is not increased by doubling. But this is an instance of the difficulty, already noted, of connecting the sum of new classes, each having mu terms, with the product of mu and nu. Sometimes this can be done, sometimes it cannot. In our case, it can be done with the boots, but not with the socks, except by some very artificial device. The reason for the difference is this. Among boots we can distinguish right and left, and therefore we can make a selection of one out of each pair, namely, we can choose all the right boots or all the left boots. But with socks, no such principle of selection suggests itself, and we cannot be sure, unless we assume the multiplicative axiom, that there is any class consisting of one sock out of each pair. Hence the problem. We may put the matter in another way. To prove that a class has Aleph terms, it is necessary and sufficient to find some way of arranging its terms in a progression. There is no difficulty in doing this with the boots. The pairs are given as forming an Aleph and therefore as the field of a progression. Within each pair, take the left boot first and the right second, keeping the order of the pair unchanged. In this way we obtain a progression of all the boots. But with the socks we shall have to choose arbitrarily with each pair which to put first, and an infinite number of arbitrary choices is an impossibility. Unless we can find a rule for selecting, that is, a relation which is a selector, we do not know that a selection is even theoretically possible. Of course, in the case of objects in space, like socks, we always can find some principle of selection. For example, take the centres of mass of the socks. There will be points P in space, such that with any pair, the centres of mass of the two socks are not both at exactly the same distance from P. Thus we can choose from each pair that sock which has its centre of mass nearer to P. But there is no theoretical reason why a method of selection such as this should always be possible, and the case of socks, with a little goodwill on the part of the reader, may serve to show how a selection might be impossible. It is to be observed that, if it were impossible to select one out of each pair of socks, it would follow that the socks could not be arranged in a progression, and therefore that there were not Aleph of them. This case illustrates that, if mu is an infinite number, one set of mu pairs may not contain the same number of terms as another set of mu pairs. For, given Aleph pairs of boots, there are certainly Aleph pairs of boots. But we cannot be sure of this in the case of the socks, unless we assume the multiplicative axiom or fall back upon some fortuitous geometrical method of selection, such as the above. Another important problem involving the multiplicative axiom is the relation of reflexiveness to non-inductiveness. It will be remembered that in Chapter 8 we pointed out that a reflexive number must be non-inductive, but that the converse, so far as is known at present, can only be proved if we assume the multiplicative axiom. The way in which this comes about is as follows. It is easy to prove that a reflexive class is one which contains subclasses having Aleph terms. The class may, of course, itself have Aleph terms. Thus we have to prove, if we can, that given any non-inductive class, it is possible to choose a progression out of its terms. Now there is no difficulty in showing that a non-inductive class must contain more terms than any inductive class, or what comes to the same thing, that if alpha is a non-inductive class and nu is any inductive number, there are subclasses of alpha that have nu terms. Thus we can form sets of finite subclasses of alpha, first one class having no terms, then classes having one term, as many as there are members of alpha, then classes having two terms, and so on. We thus get a progression of sets of subclasses, each set consisting of all those that have a given finite number of terms. So far we have not used the multiplicative axiom, but we have only proved that the number of collections of subclasses of a is a reflexive number, that is, that if mu is the number of members of a, so that 2 raised to the mu power is the number of subclasses of a, and 2 raised to 2 raised to the mu power is the number of collections of subclasses, then provided mu is not inductive, 2 raised to 2 raised to the mu power must be reflexive. But this is a long way from what we set out to prove. In order to advance beyond this point, we must employ the multiplicative axiom. From each set of subclasses, let us choose out one, omitting the subclass consisting of the null class alone. That is to say, we select one subclass containing one term, α1 say, one containing two terms, α2 say, one containing three, α3 say, and so on. We can do this if the multiplicative axiom is assumed, otherwise we do not know whether we can always do it or not. We have now a progression, α1, α2, α3, and so on, of subclasses of a, instead of a progression of collections of subclasses. Thus we are one step nearer to our goal. We now know that, assuming the multiplicative axiom, if mu is a non-inductive number, 2 raised to the mu power must be a reflexive number. The next step is to notice that, although we cannot be sure that new members of a come in at any one specified stage in the progression, α1, α2, α3, and so on, we can be sure that new members keep on coming in from time to time. Let us illustrate. The class α1, which consists of one term, is a new beginning. Let the one term be x1. The class α2, consisting of two terms, may or may not contain x1. If it does, it introduces one new term. If it does not, it must introduce two new terms, say x2, x3. In this case, it is possible that α3 consists of x1, x2, x3, and so introduces no new terms. But in that case, α4 must introduce a new term. The first new classes of α1, α2, α3, and so on up to α contain at the very most 1 plus 2 plus 3 plus so on up to new terms, that is, the product of nu with nu plus 1 divided by 2 terms. Thus, it would be possible, if there were no repetitions in the first new classes, to go on with only repetitions from the nu plus 1th class to the product of nu and nu plus 1 over 2th class. But by that time, the old terms would no longer be sufficiently numerous to form a next class with the right number of members, that is, the product of nu and nu plus 1 divided by 2 taken as the sum with 1. Therefore, new terms must come in at this point, if not sooner. It follows that, if we omit from our progression α1, α2, α3, and so on, all those classes that are composed entirely of members that have occurred in previous classes, we shall still have a progression. Let our new progression be called β1, β2, β3, and so on. We shall have α1 is equal to β1, and α2 is equal to β2, because α1 and α2 must introduce new terms. We may or may not have α3 is equal to β3, but speaking generally, β will be α, where nu is some number greater than mu, that is, the betas are some of the alphas. Now these betas are such that any one of them, say β contains members which have not occurred in any of the previous betas. Let γ be the part of β which consists of new members. Thus we get a new progression gamma sub 1, gamma sub 2, gamma sub 3, and so on. Again, gamma sub 1 will be identical with beta sub 1 and with alpha sub 1. If alpha sub 2 does not contain the one member of alpha sub 1, we shall have gamma sub 2 is equal to beta sub 2, which is equal to alpha sub 2. But if alpha sub 2 does contain this one member, gamma 2 will consist of the other member of alpha sub 2. This new progression of gammas consists of mutually exclusive classes, hence a selection from them will be a progression. That is, if x sub 1 is the member of y sub 1, x sub 2 is a member of y sub 2, x sub 3 is a member of y sub 3, and so on. Then x sub 1, x sub 2, x sub 3, and so on is a progression and is a subclass of alpha. Assuming the multiplicative axiom, such a selection can be made. Thus, by twice using this axiom, we can prove that, if the axiom is true, every non-inductive cardinal must be reflexive. This could also be deduced from Zermelo's theorem, that, if the axiom is true, every class can be well-ordered. For a well-ordered series must have either a finite or a reflexive number of terms in its field. There is one advantage in the above direct argument, as against deduction from Zermelo's theorem, that the above argument does not demand the universal truth of the multiplicative axiom, but only its truth as applied to a set of N classes. It may happen that the axiom holds for N classes, though not for a larger number of classes. For this reason, it is better, when it is possible, to content ourselves with the more restricted assumption. The assumption made in the above direct argument is that a product of N factors is never zero, unless one of the factors is zero. We may state the assumption in the form N is a multipliable number, where a number nu is defined as multipliable when a product of nu factors is never zero, unless one of the factors is zero. We can prove that a finite number is always multipliable, but we cannot prove that any infinite number is so. The multiplicative axiom is equivalent to the assumption that all cardinal numbers are multipliable. But in order to identify the reflexive with the non-inductive, or to deal with the problem of the boots and socks, or to show that any progression of numbers of the second class is of the second class, we only need the very much smaller assumption that N is multipliable. It is not improbable that there is much to be discovered in regard to the topics discussed in the present chapter. Cases may be found where propositions which seem to involve the multiplicative axiom can be proved without it. It is conceivable that the multiplicative axiom in its general form may be shown to be false. From this point of view, Zermelo's theorem offers the best hope. The continuum or some still more dense series might be proved to be incapable of having its terms well ordered, which would prove the multiplicative axiom false in virtue of Zermelo's theorem. But so far, no method of obtaining such results has been discovered, and the subject remains wrapped in obscurity. End of chapter 12.